having me here. Thank you, Thomas, for organizing this, and Johannes for all your work. And it's been so great so far, and just really nice to meet those of you I've met. Hopefully, I get to meet some more of you in the next couple of days. So what I want to share with you today is an iteration on a computational model that Thomas and I originally proposed, that you can see in the appendix of his book. And the aim of this, if I can get this to work, the aim generally is ultimately to arrive at a computational explanation of MPE. And the question is, why would we maybe want to do that? We've had a lot of discussion about this already. So I think this first point is probably already clear to everyone that like MPE provides a very interesting data points that any theory of consciousness must account for. So it's kind of interesting from just a theory of consciousness point of view. But to kind of put my cards on the table here, for me, what is almost more interesting or more exciting about this kind of work is what I've been calling a laser pointing at the moon. So this idea that these computational models can provide a new language, a really precise and accurate language to be pointing towards an experience that we can access in our own consciousness. So it's this idea that really understanding consciousness, there's this conceptual level of it and building these theories, and that is obviously really powerful and useful. But then there's this really embodied direct recognition of consciousness, which I think is almost even more valuable. And I sort of take a pragmatic stance on this work as being in aid of that rather than a kind of metaphysical project. So I'm just going to give a very quick introduction to the free energy principle and why we would want to use that for this kind of work. I need to give you a little bit of context for how the deep active inference modeling works to be able to build this up. And then I'm going to just go through some of the phenomenology of minimum phenomenal experience and show how we might translate that into a computational model that then starts to build up this story of what MPE might be computationally, or at least the beginnings of a story there. So from the free energy principle to computational phenomenology. So I'm assuming the free energy principle, and one of the questions you might ask is like, why, right? And I want to make a very pragmatic point about this. I mean, there's a bunch of kind of maybe, I guess, more metaphysical or more empirical reasons why you might want to use this. It's very, it's working out very well in a lot of the literature and psychology and neurobiology. But for me, the really interesting part is something that Vanya actually wrote about very nicely, called the dual information geometry. So I'll get to that. So the story of the FEP kind of starts with this setup. So you basically have the environment that we denote eta here. I don't know if you can see my mouse. Yeah, and the agent that's separated by this blanket B and has some internal states mu. And so it's a very, very simple setup to begin with. And then you make some additional assumptions that this thing persists through time, right? And you can split the blanket states or the blanket into two further partitions, the sort of sensory and active paths. And apologies in advance, I'm going really, really fast here, so don't worry too much about picking up the whole thing. But the point here is that when you do this, you can actually derive flow equations for these different parts of a system. And you'll see this in the active inference literature, and it'll end up looking something like this. So we apply it to the brain, and you end up getting these equations for the internal states of the system as tracking the external states of the system through this free energy minimization process. So the reason I'm showing you these equations here, and don't worry about understanding the equations too closely, is that you'll see them written like this in some parts of the literature, and then you'll see almost exactly the same diagram written like this in a very adjacent part of the literature. And so what is the difference here? On the left here, you can see that the equations are about the states themselves. They are about the internal states and the active states per se, right? So this is more of a thermodynamics of the states. Whereas here, what you're seeing is the equations of motions of the beliefs parameterized by those states. And this really is the really nice quality about the free energy principle. And this is the kind of notion of Bayesian mechanics that you can derive from the free energy principle, where you get equations of motions for both the internal states and the beliefs parameterized by those internal states. And that's actually the next slide, but what you'll see often is the diagrams like this, where you have the kind of internal states mu, and then you get these nice little thought bubbles, and these are the beliefs about the external states eta, parameterized by the internal states. So this is the kind of notion of this dual information geometry in Bayesian mechanics. So this is pulled from a paper by Vanya and Carl and Hobson, and they kind of describe this in terms of the so-called intrinsic information geometry and the extrinsic information geometry. And again, the exact details of the formula are not too important for us here, but I'm just trying to emphasize this point that in one formalism, we get this really cool thing. And I think it's very novel in the sense that you can have a dual interpretation of the internal states of a system. You can describe them in terms of the thermodynamics, so the intrinsic geometry, the flows in time of the internal states. And then you can also describe the dynamics of the internal states in terms of the beliefs that those states parameterize. And the formalism itself gives you this very principled linking between these two. So in a computational phenomenology that's based on the free energy principle, the assumption that we're making is that we're linking the phenomenology to the belief dynamics, right? And that's the key point. So we can say, ask, what posterior belief are we using to model a particular aspect of phenomenology? That's kind of the assumption that's being made here. And again, it's not a metaphysical claim, unless you want it to be. For some people, it is. But for me, here, I'm just making a pragmatic claim, which is that we're making the decision to model the phenomenology as the extrinsic dynamics or as the belief dynamics using the free energy principle. And what that allows for, and this is from a recent preprint, my colleagues Juan Diego, Jakob, Julian, and Antoine, it allows for this interesting new mathematics for doing neurophenomenology, where you leverage this dual information geometry to fit a model of some phenomena from the phenomenology on one side, so you can kind of see that coming through here, fitting the extrinsic dynamics, and from the neurobiology, fitting the intrinsic dynamics. But importantly, one same model at the heart of it that you can fit from both sides, and it gives this nice quality for doing consciousness science or research into some phenomenon. So if we place at the center here a model of MPE, what I'm going to do now is just talk you through how we might do this work of linking the phenomenology into the extrinsic dynamics of the model. And luckily, we have Thomas's really nice project with a bunch of the phenomenology from MPE that we can start to do this work. So how do we do that? So now we're moving from Bayesian mechanics into active inference, where we are going to make the assumption that we can model all these processes using a partially observable Markov decision process, which gives rise to this kind of really nice tractable language for actually doing this. So just very quickly, so you can understand the logic a little bit, for some people, you've seen a lot of these, but for those who haven't, the idea here is that S is, this is a Bayes graph that shows the belief updating process for inference. And S is basically the agent's inference about the states of the outside world. And so you're taking in observations from the world, you're combining it with some beliefs about how observations relate to states and some prior, and then you get some posterior distribution. Now, the important point here is that the posterior here that we're calculating numerically, that we have a model of, that's what we're relating to the phenomenology. So we're looking for ways to tie these things together. So we can start to extend this out. And Aline was talking about this yesterday around precision weighting. And so each one of these parameters of the model, so A here, the likelihood mapping, you can have a belief about that, right? A confidence in that. And this is also something that the agent can optimize. And this particular parameter, as was already discussed, is being related to attention. So here you can start to hear already the sort of the links between the phenomenology and the parameterizations, right? So we can kind of continue building this out. And again, don't worry too much about the equations, but just kind of show the structure of this. Once we start moving in time, we get anticipation. We have beliefs about the transitions that are parameterized by policies that are dependent on free energy minimization. But it starts to build up this really tractable language for talking about action and perception. And importantly here, we still have the precision of this likelihood mapping, which we're relating to attention. But in this case, attention is just sort of being updated moment by moment. So what if we want to have something like deliberate attention, something like mental action? If you were to ask the question, what should I pay attention to, or how will my experience change when I pay attention? Then we need another layer. And this is the notion of parametric depth that we introduced a few years ago. And it's the idea that you could take as the basis of inference parameters of your generative model. So this starts to speak to this idea of modeling the modeling process. And I'll kind of get into that as we go along. But you can see that if we add these layers, then you can have a phenomenology of attention, because now you're doing a state inference about these parameters. And so this is kind of how it would look in the more Bayesian mechanics sort of lens. But you can keep going. And so you could add an additional level where this is something like, if I were to ask you the question, to what extent are you aware of where your attention is right now? You went and did something to answer that question. What you went and did is you went and inferred this higher order state, which is, how precise is my mapping of my attentional state. And so this gives a kind of notion of meta-awareness, or that was kind of the proposal. And so at this point, most people who see this start to worry, right? What about this infinite regress problem? Can you just like keep going up? It's just like meta. I just put those concerns aside. It doesn't happen because if you're inducing more complexity as you go up, and you need to gain in accuracy for being able to keep that model. So you do actually top out quite quickly. And I just lifted this from Ronald's talk yesterday. He's not here, but this idea that as you go up, it becomes more and more abstract. And so by modeling, if you think about what's happening at each level going up here, it's a precision of a precision of a precision, a variance of a variance of a variance. And so you're eventually going to just top out in terms of what's useful to model. So don't worry about the infinite regress. And so that was the basis of this model that we originally proposed in Thomas's book. And this was kind of like a simplified version of it. And we were really just emphasizing this inferences on the basis of these likelihood precisions going up, and talking about how there's like an awareness of how aware you are of how aware you are. And the innovation, or like the iteration here that I want to share with you, is extending this and generalizing this out to other parameters in the generative model, right? So what we saw just now was that I was taking the likelihood precision as the basis for second order inference, but we can extend this treatment to all the parameters of the generative model. And now we can think of this higher order state factor as being a sort of generalized mental state factor, where now I'm making inferences about other kinds of parameters in my modeling process. And if we could relate this to attention, the likelihood precision to attention, it opens the question, what kinds of phenomenology can we relate to these other forms of precision inference? So it kind of opens the door for cataloging aspects of phenomenology, which is what we can do with the MPE data set, and start seeing how we could fit this in. So that's what we'll do. So the idea is, we're assuming the active inference framework, we're extracting these core features of MPE, and we're just bringing them into the model, and it starts to build up a picture. So it's very phenomenology first. And what's interesting is if we just formalize a few of these aspects, some of the other aspects start to fall out as predictions of the computational model. So I'll just show you, again, very quickly how it works. But we'll just look at meta-awareness, this notion of ease and this notion of openness, to show how effortlessness, timelessness, and I think it lines up with your account. I'll be interested to hear what you think, and even up to this notion of no self. So the model that I'm sort of proposing in this latest iteration looks like this. This is the model structure. You'll notice that a level got dropped. I can talk about that. But basically what we're doing is we're taking a few additional model parameters as the basis for second order inference. And that gives rise to a kind of more rich phenomenological account of what's going on here. So to start with the notion of meta-awareness, we kind of already talked about that. In MPE, there's also these notions of clarity, of wakefulness, and that is all captured by having a very high precision over this higher order likelihood mapping, because that gives rise, at least computationally, to very accurate and precise, opaque, we would say, perception of my own mental states. And when I say mental states, it's like inferences about the parameters of my own generative model. That's what we're talking about. So these second order layers are really modeling the modeling process, because you are modeling the parameters themselves. But that's kind of a little bit unsatisfactory. And because in meta-awareness is also this quality of reflexiveness. There's this feeling of it being aware of awareness. And so what could that mean computationally? And I just want to point out that it actually is captured here. So there's three sources of reflexivity already in the computational model that you see here. So by increasing this parameter, by making this precision high, what you're giving the agent is the ability to perceive the parameters of its generative model. Now, the parameters of the generative model are what come together to form the posterior distribution. They are part of the inferential process. And so by perceiving the parameters of the inferential process, what the agent is becoming aware of is the process of becoming aware of their experience. So there's already a bit of reflexivity there. They're aware of the emergence of the posterior, or the parameters that are going into the emergence of the posterior. But also you, oops, wrong computer, you add state inference about that parameter. And now you end up with something that feels like an awareness, right? An awareness up here, because I'm aware now, I have this perceptual inference up here, of the degree of awareness, which is the value of my actual precision, of the process of becoming aware of my experience down here. So it gets this very kind of loopy quality to it that maybe isn't immediately obvious at first hand. And also you have to remember that the message passing is going in both ways, right? So the actual way that the information flow is happening in these things is top down and bottom up. So there is this kind of like loopy message passing. And one of the kind of feelings that might be coming up is this impression of it being meta, like a perspective, almost like a homunculus kind of looking down and like it's creating like a separation within oneself. And I just want to kind of alleviate that concern as well, because although there's many layers, there's only one experience. And this is a kind of extract from a paper I wrote with Lance. And what we show from a Bayesian mechanics point of view is that despite there being many layers in this hierarchical kind of structure, there is because it does top out at that top level, all the beliefs in the entire generative model are captured in one variational density. And so there is a gestalt experience of this whole thing, of all the awareness of the awareness and everything happening in one place. So don't be fooled by the structure and thinking that it's somehow disjoint from myself or like a homunculus kind of story. It is all flattened into one Markov blanket at the end. So the next kind of quality that we could introduce here is this notion of existential ease, which I've been modeling as a flattening of the prior preferences, which is this precision parameter over the preferences C. And what's interesting with this is if we were to do this, it really just drops out the pragmatic driver of action in the generative model. And so an agent that has a very flat prior preference is going to experience a sense of stillness. I really like this quote. I was able to perceive bodily sensations, but I did nothing with them. And that kind of speaks to what would happen computationally if we were going to flatten this. So I'm capturing this notion of existential ease as a top-down modulation of the preference precision. And so you can kind of see how I'm building up a bit of a story from the phenomenology here. I really like the language of existential ease in relation to the preferences, because actually the preferences define the sort of phenotypic needs of the agent. They are the pullback attractor of the agent. They are what defines the homeostatic regulatory set points, and they are what allows the agent to continue to exist. So by flattening this, existential ease really kind of does seem like a plausible description. So, and again, apologies for going quickly through this, but we can keep doing this with different parameters. And so here we've got this. I'll skip this. I'll skip the epistemic openness because I really want to speak to how this kind of unfolds into a sense of effortlessness, timelessness, and this epistemic space. So the effortlessness. Let's see. But I do want to respect the time too. But so the effortlessness interestingly falls out as a prediction of the model. Once you've made these formalizations that I already described, effortlessness seems to be a prediction. And here, if we just adopt the view that was presented by Thomas, Emma, Carl, and Giovanni, that effort can be formalized as this divergence between the habits and the expected free energy, effectively. When you look at the formalizations I've already done so far, you can see that, well, effortlessness, as they've defined, would happen under these specific conditions, right? Mathematically, that term, the effort term here, actually goes to zero if one of these conditions are met. You know, if G is uniform or similar for all the policies, or if the amplitude is different. And what's interesting is with the formalizations I've already done so far, and I won't kind of get into the detail here, but you can basically show that this follows, right? So effortlessness seems to be a consequence of having cultivated a high degree of meta-awareness and a high degree of equanimity and letting go. So that's interesting. And the reason why I want to point this out is that one of the criticisms or concerns one might have is that this is kind of mathematical storytelling in the sense that we're just kind of linking things kind of willy-nilly. But because you're linking them to parameters that have relationships with each other, there are consequences to the assumptions that you're making that are constrained by the model structure. And so your story better be coherent because there's no way around it. You can't gerrymander it, or there's limits to how much you can gerrymander it. The timelessness is really interesting. So there's two qualities of timelessness that are reported in MPE. There's this kind of ever-changing now experience, sorry. And then there's also this more sort of pure timelessness, this sort of an eternity experience. And the ever-changing now, I think, is pretty well like accounted for by this flattening of the temporal depth that Liam was already talking about, and the fact that, and I skipped this slide, but the kind of dropping of the precision over the expectations. So you have this like no anticipation of what's going to happen next, and yet your posterior is being updated and is changing. So there's this kind of changing present moment. But how do we make sense of the kind of eternity experience, the real timelessness? And in this paper that we preprinted just a couple of days ago, actually, we make this proposal that temporal duration specifically can be related to the information length of the belief updating. And so a timeless experience, or an experience with no temporal duration, but perhaps still persistence, would be a situation where this information length goes to zero. So where moment by moment your posterior beliefs are not changing so much. And why would that happen during MPE, or at least during an absorption? Well, I can point again to this figure by Ronald, which is that when you get up to these higher abstract levels, there is just less change. It's a variance of a variance of a variance. And so if you are attenuating all the other levels and just performing inference at this higher level, the amount that your beliefs are changing moment by moment is very, very, very small. And if we accept or we adopt this view that is that belief updating that is the phenomenology, or it can be modeled as the information length, then it follows from the account so far that MPE during an absorption would be timeless, or at least lacking duration. And so finally, where this kind of all comes together for me is this notion of modeling the epistemic space, or modeling the modeling process. And this is a quote from Thomas, that this idea of modeling the epistemic space seems to be a really nice candidate for what MPE might be. The epistemic space is just this space of all the possible experiences. At least that's how I've been understanding it. And we've seen the experience is the posterior mathematically in the generative model. So we can think of a computational account of the epistemic space as being the statistical manifold of all possible posterior beliefs, right? So statistical manifold is just one where every point is a probability distribution. The dimensions of this manifold would be all the parameters of the generative model, because that's what comes together to form the posterior distribution. So now we have a mathematical object that is a candidate for the epistemic space, the statistical manifold of all possible posteriors. And then the question is, what would it be like to model this space? What would that mean? Well, that's exactly what parametric depth, I would argue, provides, right? Because what you're doing is you're developing a generative model of a coarse graining of all your model parameters, right? So this model at this level is a predictive dynamical model of the space of possible posteriors that you can experience. And so through this mechanism, through experience, through time and training and paying attention, we build this model of the epistemic space. The interesting thing here is it introduces another interesting recursion into the model, where you're modeling the dynamics of your own modeling process, as well as modeling the space itself. So it really lines up with something Edmundo was sharing. And also it implies this idea that awareness is empty, because the model of this space is not the space itself. It is still just a generative model. And so here, right in the mathematics, we can see that even pure awareness itself, if that's what if that's how we're describing it, is constructed, is empty. The final thing I want to just tackle, because I feel like this is probably the most difficult thing to account for in these models. Like how does the zero-person perspective emerge, and why does it emerge? I want to propose that this is different to the flattening of the self-narrative construct that happens through temporal flattening. And part of the reason for that is that people report having this experience of zero-person perspective in normal waking life, even when they're planning things and going about their life. I relate this to the notion of fourth path in sort of Theravada Buddhism, or at least in Daniel Ingram type fourth path or arhantship, this notion of centralist experience. What is going on here? So the sense of the first person perspective is an experience. So we can ask the question, what's the related posterior belief, right? And a posterior belief is an explanation for the cause of some observations. So the question becomes, what are the observations that the agent might attribute the self as cause of? And so the idea here is that the second order observations of my own generative model might be something that I have prediction errors about, right? Before I've actually built up that model and have good predictions about it, there's going to be free energy that I'm incurring because I don't actually know how my modeling process works. And so the hypothesis that I'm putting forward is that the first person perspective is the experience of the posterior explanation of the unperceived or unmodeled dynamics of the generative model parameters. So that was kind of a heavy sentence, but the idea is that you're perceiving your own mind, but you don't have a good model of it yet. And so you're making prediction errors. So you explain away those prediction errors as being caused by you, because in a sense they were about your internal states. But you're appealing to an abstract self-concept in the kind of sweeping under the rug of those prediction errors. But as we continue, and in MPE, what we just described, right, is that the agent is developing a really accurate model of their epistemic space, of their generative modeling process. And as that happens, those prediction errors go away in favor of an accurate model. And therefore, the need for this ad hoc posterior explanation of that goes away and is pruned in a moment of Bayesian model reduction. And what we might experience there is just, experience as being the same as it was in a sense, although I'm seeing now clearly how it's going on and seeing that I don't need to attribute some self-concept to any part of it. So this is very kind of what's the word I'm looking for? Preliminary or hypothetical, open to feedback. I'm very curious how that lands. So in summary, we can kind of work through, and I didn't go through all of them here, but you can work through the phenomenal characters, translate them into these mathematical characteristics or these mathematical constraints in the generative model, and kind of end up at this conclusion, effectively, that I see kind of MPE as a result of this generative model mastery, where they're developing a really opaque model of their own modeling process. And this provides the possibility for tuning and self-tuning, the whole free energy minimization process, which can lead them into a place of very low free energy, particularly through this emphasis of becoming aware of something that was always there, right? The space of awareness, giving this kind of perfect predictive feedback loop, right? Aware, still aware. And there's this nice phrase from Thomas's counterfactual invariance that sort of captures this feedback loop. And so it connects this minimal and minimal phenomenal experience to this very specific opportunity for minimal free energy that arises through self-modeling. And as a final word, I mean, the next steps here would just be to implement this into a simulation, prove out some of the predictions, and also to harken back to the beginning of the presentation, make some neurobiological predictions as a result. So there's a whole rich literature on the neural process theory that accompanies this, so we can make ready predictions from this model into empirical experimental settings, and that would be kind of the next step. Thank you.